In 2005, a single block of text brought down the largest social media platform in the world. This was the MySpace worm. A modified user profile contained a script that forced anyone who viewed it to unknowingly copy the exact same code onto their own page, creating a cascading chain reaction across the network. The author of that payload was Samy. He wrote a snippet of JavaScript designed to force anyone who visited his profile to automatically add him as a friend and append the phrase, "But most of all, Samy is my hero," to their bio. The infection spread at an exponential rate. Within 20 hours, the script had executed on over 1 million individual machines, forcing MySpace to take its servers offline to stop the propagation. didn't break through a firewall or exploit a flaw in the server's operating system. He simply typed code into a standard profile input field, and the application accepted it as safe text. By storing that untrusted input permanently, the platform's own back-end infrastructure became a distribution hub for malicious code, weaponized against its own user base. In reflected XSS, a hacker tricks users into clicking links. The payload bounces off the server and executes. Stored XSS bypasses users entirely. The payload commits directly to the database. Attackers don't hunt victims. The compromised website automatically delivers victims to the payload. Any feature that accepts dynamic user input and displays it later is a potential vector. This includes blog comment sections, customer relationship management systems, message boards, and user profiles. To stop this self-contained exploit, developers have to trace the exact lifecycle of the data, from the moment it enters the application to its final execution in the browser. The lifecycle begins at the application's entry point, usually with a standard HTTP POST request. A POST request is a network protocol method used to send data to a server to create or update a resource. Normally, this request carries benign data. A user types a normal message like "great article" into a blog comment field, hits submit, and the text is packaged into the request parameters. The attacker modifies this request, replacing the benign text with a payload of raw JavaScript wrapped in a standard HTML script tag. The critical failure happens at the application tier. The server receives this input and processes it without validation or sanitization, meaning it never checks if the incoming text contains executable commands. The application logic takes that raw script and executes a standard database operation, like a SQL insert command. It permanently commits the attacker's code into a structured database table alongside legitimate comments. The payload is now stored as static data within the database. It will remain there until the application logic executes a query to retrieve and display that specific record to another user. By failing to inspect the incoming data, the application has turned its own database into a staging ground for a client-side attack. Many developers assume a web application firewall, or WAF, will catch these injections. A WAF is a security system that inspects incoming web traffic to filter out known malicious patterns, often using simple blacklists that block exact strings like the word script. Attackers anticipate these rigid blacklists. They use advanced structural manipulation to disguise the payload, altering its syntax so it slips right through the security grid. One method is the use of a polyglot payload. A polyglot is a specialized script crafted to be perfectly valid syntax across multiple interpreters. It can be read as valid raw HTML, JavaScript, and CSS simultaneously, thoroughly confusing standard security filters. Another common evasion tactic targets the way web browsers try to be helpful when rendering broken or improper HTML tags. Attackers will inject JavaScript event handlers, like the onError method, inside a malformed image tag. When the browser predictably fails to load the non-existent image, it triggers the error event and executes the hidden JavaScript instead. If the application does not perfectly implement HTML entity encoding, the process of converting characters like brackets into safe text equivalents, these evasive payloads will successfully make it to the database. Perimeter blacklists fail because they rely on matching known bad shapes. They cannot anticipate every morphological variation of executable syntax. The final phase shifts to the victim. An authenticated, logged-in user navigates to the compromised blog post or user profile. The server receives the request, queries the database, and blindly extracts the stored comment. It embeds the attacker's payload directly into the outgoing HTML response and sends it back to the user. The victim's browser begins parsing the document object model, or DOM. The DOM is the internal structural map the browser builds to render a web page. It reads the normal HTML nodes, hits the injected script, and obediently shifts into execution mode. Because this payload was delivered by the trusted server as part of the official page source, it executes automatically. The script now runs entirely within the context of the victim's authenticated session. The script's objective is accessing the document.cookie variable to steal the user's active session token. It then silently transmits this stolen token via a background request straight to a remote attacker-controlled server. The application architecture has failed its users. The attacker achieves full account takeover, and the victim never had to click a suspicious link. Mitigating Stored XSS requires a defense-in-depth architecture. This strategy starts at the application's entry points, cleaning the data immediately upon arrival. The core principle here is strict input validation and sanitization. The server must verify that the incoming data exactly matches the expected format before doing anything else with it. Instead of relying on easily bypassed blacklists, developers must use whitelisting. This means the application is configured to allow only explicitly known good characters, rejecting everything else by default. When applications do need to accept some HTML, like bold or italic text in a comment, developers use established parsing libraries like HTML Purifier. These libraries strip out any dangerous tags or attributes before the data ever touches the database. During this sanitization phase, it is critical to escape all dynamic content. Escaping converts special characters, like the less than and greater than signs, into their safe text equivalents. This forces the browser to interpret the data strictly as visible text, neutralizing its ability to execute commands. Treating all user-supplied data as inherently hostile ensures the database is populated only with safe text, stopping the injection phase completely. Application tier defenses are written by humans, and humans make mistakes. To account for this, you need a secondary, fail-safe layer of defense at the application's exit. This is the role of Content Security Policy, or CSP. CSP is a security standard used to restrict exactly which dynamic resources are allowed to load and execute in the browser. Developers configure CSP headers to explicitly instruct the browser on permitted behaviors. They specify an exact whitelist of approved domains where scripts are allowed to originate. A strong CSP strictly enforces the same origin policy, outright blocking the execution of unauthorized inline scripts. Even if a complex payload persists in the database, when it tries to execute, it hits the CSP boundary and is instantly blocked. This creates a robust, dual-layered architecture. You clean the data aggressively on arrival at the server, and you restrict its execution context upon delivery to the browser. Stored XSS exploits a chain of trust violations. By enforcing strict zero-trust policies at both the application and the browser levels, developers permanently break that chain.